Okay, everyone, let's continue to talk about the hydrolysis of esters in basic condition, which is called saponification. So we need to use an excess amount of strong base to decompose the ester, or you can say to hydrolyze the ester. The mechanism is here, but we don't want to talk too much about the mechanism. We try to understand the basic hydrolysis in a similar way as the acidic hydrolysis. We still break down the ester. We add OH to the left side, so it will change into the acid fragment. But under basic condition, the acid will be further neutralized, change into the conjugate base. And the right part, the alcohol part, is still the same. It get into the alcohol part. So this is the basic hydrolysis. So there are two, differences. The first one is the acid is further neutralized. The second one is because the acid is neutralized, so the reaction is not reversible anymore. So the saponification, basic hydrolysis of esters is irreversible because the conjugate base is away from the system. So this is how it is different from the acidic hydrolysis. So next, we can briefly talk about why the process is called saponification. Saponification actually is the soap making process or the soap synthesis. So the name of saponification is from the soap making. Why is it related to soap? We need to have a look. What is the traditional way to make soap? So we use fat or oil. Both are triglyceride. What is a triglyceride? Basically, it's esters. Did you see the ester groups? Since it's an ester, it is made by alcohols and acid. So we can try to figure out what are the acids here, what are the alcohols here. They are not hard to find. The alcohol actually is a trialcohol. It's called glycerol, which is commonly added to the makeups because glycerol has so many OH groups. So it can make strong hydrogen bonds with water. So this is why it can absorb water from the air, which can help the makeup to keep humid when not dry. And then there are three acids, and those acids are all long chain carboxylic acids, which means those R groups have about 13 to 21 carbons, including the carbon in the COOH. There are 14 to 22 carbons. So they are commonly called fatty acid or phthalate acid. So this is why the name actually is also from the fat or the oil. We can later discuss the difference between fat and the oil. So if we add a strong base and heat the system, the fat and oil, those triglyceride can hydrolyze, change into the glycerol and the conjugate base of the fatty acid. And the conjugate base of the fatty acid are actually the component of the soap. You probably can make, soap in your kitchen. You just need to get some oil for cooking, and then you probably need to get some base from the chemistry lab. And then you heat it, and after the reaction, you get two layers. The first layer is kind of the glycerol. The second layer is the soap. The soap is a common used household amphiphile or amphiphilic compound. Amphi means two. Philic means affinity has affinity to something. So which means it has two different affinity to different stuff. It means one side is hydrophilic, water loving, basically is polar. Another side we call lipophilic, or we can say hydrophobic, which means doesn't love water but love fat, fat loving. So let's have a look at the structure of the conjugate base of the fatty acid. So there is a long non-polar chain made by carbons. And in the end, there is a carboxyl group, right? Now it's neutralized, turned into conjugate base. So this side, obviously, is polar, right? It's ionic even, so it definitely is polar. So one side is non-polar, another side is polar. So this is called amphiphile. So amphiphile can help the dirt, especially those water-insoluble dirt, to dissolve in water. So this is basically the mechanism of the soap. You can do some further homework by yourself to check how does the soap work. I will recommend you to try to connect the mechanism of the soap with the bilayer structure of the cell membrane, because the cell membrane is also made by two layers of amphiphiles. So the next reaction is about the oxidation of alcohols and aldehydes. Before we introduce the oxidation, we want to slightly differentiate the different types of alcohols. We call it primary, secondary, and tertiary. Basically, is determined by the number of carbons attached to the carbon bonded to the OH. We call this carbon into alpha carbon. Basically, in organic chemistry, the carbon directly bonds to the function group. It's called alpha carbon. So we want to look into the number of carbons attached to the alpha carbon. So let's have a look. OH is here. So this is the alpha carbon. So there is only one carbon connect to the alpha carbon. This is called primary alcohol. And this is also the alpha carbon, but there are two carbons connect to the alpha carbon. So this is why it's called secondary. If there are three carbons, it's called tertiary alcohol. You can try to think about whether we have the quaternary alcohol, which means the alpha carbon is connected to four different carbons. The question is here, right? Basically, the answer is no, because carbon can only make 4 bonds. It cannot make 5 bonds, right? As we mentioned before, if the hydroxyl group is connected directly to a benzene ring, this is called phenol, because it's much more acidic than the regular alcohols, and also have some special chemical properties. So this is why there is a new name for this type of compound. You may also see the primary alcohol is expressed as 1 degree alcohol, secondary is 2 degree, tertiary is 0 degree or 3 degree, and we also have methanol. The alpha carbon has no carbon attached, so we can call it 0 level of alcohol. And then we can further have a look at the different level of alcohol. How are they oxidized? Let's start from the primary alcohol. The primary alcohol can first oxidize into aldehyde. Let's have a look at this step to see what is the change of the bonds. Oxidant is added. Okay, I think it's not hard to realize. First, a double bond is added here, which means this hydrogen is gone. This hydrogen is also gone, right? So you're losing a H2. Obviously, it will not, have hydrogen gas produced, because this hydrogen gas will bind with the oxidant, change into water. So since it's a primary alcohol, which means there are 2 hydrogens connected to the alpha carbon, which means in the aldehyde, there's 1 H left. So with this H, the aldehyde can be further oxidized into a carboxylic acid. What did it change? A oxygen is added in between the C and H, which is this one. So this is the second step of the oxidation. So let's have a brief summary. Primary alcohol can be first oxidized into aldehyde, and the aldehyde can be further oxidized into carboxylic acid. So can we, make the reaction stop in the intermediate of the aldehyde? The answer is yes. We try to avoid the use of the strong oxidant because they can easily oxidize the aldehyde and turn into the final product, the carboxylic acid. If we use a weak or a mild oxidant, we can stop at the aldehyde process, the aldehyde step. So this is the oxidation of the primary alcohol. If we use secondary alcohol, after this H is gone, a double bond is formed here, we got a ketone, which has no H like in the aldehyde. And the ketone, since there's no H like that, it cannot be further oxidized because there's no way for you to put an oxygen in between two carbons. You can only put the oxygen in between the carbon and the hydrogen in the aldehyde group. So this is the major difference of the secondary alcohol. We can further look at the oxidation of a tertiary alcohol. This is the tertiary. As you can see, there's no way for you to remove a hydrogen from here because there's no hydrogen here. So you cannot add a double bond here. So otherwise, this carbon will have 5 bonds. So this is why the tertiary alcohol cannot be easily oxidized like the primary and the secondary alcohol. I think we can have a look at this USNCO example from the local 2017. Which compound react readily with the chromium-6 reagent? Chromium-6, manganese 7+ are strong oxidant commonly used in both inorganic chemistry and organic chemistry. A is a primary alcohol. So I think this is a good answer. It can be oxidized into aldehyde first and then acid. So I think you guys can take maybe a few seconds to draw the structure of the aldehyde and the acid. B is a ketone, so this one cannot be oxidized. C is a carboxylic acid. It cannot be oxidized either. D is a tertiary alcohol, so as we discussed, it cannot be oxidized either, right? So I think we already answered the question. So you guys can, further take some time to have a look at the summary. From the primary alcohol, change into aldehyde first, and then finally carboxylic acid. So if we recall the oxidation level, this is +1, this is +2, this is +3. So similarly, secondary alcohol can be oxidized into ketone, but it cannot be oxidized into the next step, right? And tertiary alcohol, it cannot be oxidized at all. So next, let's have a look at the oxidation of the aldehyde. Actually, aldehyde is even easier to be oxidized compared to the alcohol. So we can still use the strong oxidant, such as the +7 manganese or the +6 chromium. The common used reagent is the acidified potassium permanganate and acidified potassium dichromate, right? So if we use this kind of strong oxidant, we can change the aldehyde into the acid. As we discussed before, there is an oxygen insert in between the carbon and the hydrogen. But you may pay attention to the color change when the +6 chromium is used. The +6 chromium is either yellow or orange. It depends. If it's chromate, it's yellow. If it's dichromate, it's orange. But after the redox reaction, the plus chromium is reduced into the +3 chromium, which is green. So if you observe an obvious color change like this, which means the aldehyde is oxidized. So this is the color change. So obviously, the ketone cannot be oxidized in this way, because there's no way to insert the oxygen. So here we talk about the strong oxidant, but since aldehydes can be easily oxidized, so we can also choose some weak oxidant. So the first option is the tolerance test, which is also called the Savomiro test. Basically, there will be a very thin layer of silver metal deposited on the internal wall of the glassware, such as a test tube or a beaker or any other glassware, which are used as a container of the reaction. So what is the weak oxidant here? It is a complex we discussed before, the diamine silver plus. This complex is supposed to be colorless because the color is related to the +1 silver. The reaction is like this. So this complexation process will not change the silver plus. And as we know, the silver plus has a D10 electron configuration. So which means all of the d orbitals are full filled. So there's no DD transition. So this is why it is colorless. If you have never heard about the DD transition, no worry, you can do some research first. We'll discuss this, in season 3 when we, explain all of the hard, challenging, and advanced problems in the USNCL locals. Okay, so the oxidant is a +1 silver in the form of a complex. The aldehyde is oxidized. The aldehyde is oxidized into the acid, but since the complex, the tolerance agent is basic, so the acid will be existed in the form of the conjugate base. And the +1 silver is reduced into the 0 silver, the silver metal, and then the silver metal will deposit on the surface. So this is why it's called Savomiro test. So obviously the +1 silver, especially in the complexation form, is a pretty weak oxidant. So there is a example. Which of the following will give a negative tolerance test? Negative tolerance test means there's no Savomiro produced, which means there's no aldehyde group in the structure, right? Let's have a look at all of the options. Acetaldehyde, which is the aldehyde with 2 carbons. Obviously, this will give a positive tolerance test. Formic acid is a carboxylic acid, but this one is very special since this one has only 1 carbon. So this group actually is an aldehyde group. So this one will also give a positive tolerance test. The next one is ethyl formate. Ethyl formate is an ester. Formate is the 1 carbon acid. So it's like this. So similarly, we can also see the aldehyde group. So this one is also positive. And finally, acetone. Acetone has 3 carbons, no aldehyde group. So this one will not give a positive test. So I think this is the answer. Glucose is a saccharide, which is a polyhydroxyl aldehyde or ketone. So if we show the structure, we'll show the very brief structure. So there are 5 hydroxyl groups, and the N is an aldehyde group. So glucose will also give a positive results. So the correct answer here is supposed to be D. Another weak oxidant is the filling solution. Filling solution is made by a complex of copper 2 plus. So the copper 2 plus is complexed with the base tartrate ligand. We don't need to care too much about the structure, but as we can see, the central copper is 2 plus because each ligand is 4 minus. So this is why it's 6 minus in total. So this is a deep blue solution because it's related to the copper 2 plus. And after it reacts with the aldehyde, this copper 2 plus can be reduced into this brick red products, which is the copper 1, the copper 1 oxide. So if we observe the blue solution change into a brick red precipitate, we can say, okay, there is an aldehyde group in the structure. So this is another way to identify the aldehyde group, which is also commonly used in biology to differentiate the reducing sugars and the non-reducing sugars. Basically, you can say reducing sugars is those saccharide with the aldehyde group. And non-reducing sugars has no aldehyde groups. So this is a supplementary to the tolerance reagent test. I think you can try to take a few minutes to write down the equation of this reaction. And I suppose we can use the RCHO to represent the aldehyde. So I will leave this as your homework. Great, I think that's everything we missed. So yeah, feel free, to subscribe my YouTube channel for more, videos coming. Thanks for your watching.